In engineering, experimental data is often used to understand how two variables are related, especially when no clear mathematical model exists. To analyze these relationships, trend analysis is used, which help predict how one variable changes based on another. A key method in trend analysis is curve fitting, which finds a mathematical function that best represents the data. This chapter introduces two main approaches: the least square method and interpolation, with a focus on discrete least squares, which help fit a polynomial function to given data points. Here comes the problem statement. In science and engineering, analyzing object shapes is often essential. However, irregular or organic forms like leaf don't suit the standard mathematical models. This raises the challenge of accuracy calculating geometric properties such as parameters or area. Manual methods by using string are simple but lack precision. As alternative, the least squares method offers a more symmetric, data-driven approach to approximate complex shapes using fitted equation. In this project, we plot a leaf shape using over 10 data points and apply the least square method in the Excel to estimate its circumference, with results shown to 4 decimal places. There are 4 objectives on this project. First, developing a mathematical model for regular and irregular shapes using experimental data. Second, understanding the least square method for curve fitting and trend analysis. Third, perform and validate curve fitting using Microsoft Excel. Last but not least, compare the accuracy and practicality of curve-fitted equations versus manual string measurements. The scope of the project, which involves focus on analysis the parameters of two-dimensional leaf shape using coordinate data extracted from the outline. The least squares method is applied to approximate the mathematical equation that represent the curve of the leaf boundary. Next, calculations and curve fitting are performed using Microsoft Excel as the computational tool. A comparison is made between the result of the numerical approximation and a manual measurement technique using a string to trace the leaf's edges. Here's 5 limitations we deals along the analysis. First, the analysis is limited to two-dimensional representations and does not account for variations of the leaf thickness or curvature in the third dimension. Accuracy depends on the precision of the coordinate data and the width of the leaf outline. Manual string measurement may introduce human error or not perfectly repeatable. The least square method assumes data points are noise-free and well-ordered, which may always reflect real-world measurements conditions. The model is specific to the selected object, which is leaf, and may not be directly generatable to irregular shapes.
Yeah. To begin, we only need a few basic items: the leaf, a pencil, and a piece of graph paper. Now, place the leaf on the graph paper and gently trace its outline. Kapoosh! Then, draw a horizontal and vertical axis. These will serve as our X and Y axis for plotting. Now, mark several points along the edge of the leaf. More than 10 is ideal. Carefully record their X and Y positions as coordinates. These points will become the foundation of our curve fitting.
So now, let's move on to the method of calculation. We will take the first 4 points that we have plotted on the leaf and take their X and Y values to calculate the x squared, the x cubed, the x to the power 4, the xy, and the x squared y values. And then we sum up all 4 values for each column, and we will put it in the form of matrix to find the coefficients of our fitted equation, which are quadratic equation. The method that we are using is the least square method. After finding the fitted equation, we will repeat this step by taking the last point that we have plotted and take 3 more points, in total of 4, to do the same thing again until we get the whole perimeter of the leaf. So here's the result that we have obtained. In total of 4 fitted equation that we have found, we calculate it using the arc length formula to get the arc length of each fitted equation. By adding all of them, we can find the estimation of the perimeter of the leaf, that is 23.8798 centimeter. Also, we already calculated the actual perimeter of the leaf using a thread and a ruler, which we have found out to be 26 centimeter. We have noticed that our estimations are not the same with the actual perimeter of the leaf, so we have calculated the error and the percentage error of our estimations, which are 2.1202 centimeter and 8.15% respectively. In conclusion, of course, errors are inevitable, but the method remains reliable. The actual perimeter of the leaf is 26 centimeter, while the estimated perimeter that we have calculated is 23.8798 centimeter. The error percentage that we got is 8.15%, and it caused by various factors. Well, to name some of them, we have limited decimal places in our calculation, which we use 4 decimal places. We also restrict our data point for a least square fitting, since we only use 4 points. We also potentially stretch the thread under force while measuring the perimeter of the leaf. And last but not least, the accuracy constraint of the ruler is only precise to 0.1 centimeter. This method provides a reliable way to estimate the perimeter despite the errors that we have encountered, since the goal of estimation is to give a general idea of the perimeter of the leaf rather than the exact precise measurement of it. Well, that is all from us. Thank you.